this is for 3D. And I will start off by playing
buildings are
from Ireland.
Am I to include the building waffles? That's rhetorical, just show me. What does that look like to you, Jarvis? Not unlike an island. In which case, the place over here. Highlight the insert.
So, sorry, I will just interrupt that for 1 second because I want to, I mean, many of you will have seen this, okay? But what I want you to focus on is not just on the movie itself, okay? Note that it was filmed when the actor was standing there and nothing of that display technology does not exist. So the actor was doing this in basically empty air and it was all composited in and it looks great and that's awesome. I want this display system, I want the Jarvis guy there, because if you look at carefully what the gestures are and so on, the interpretation of the gestures is magic. There is the same gesture that does different things in different contexts, recognizing what is displayed there and so on. So there's a lot of interesting things. Sorry for interrupting this for a second here, but I'll continue playing it, but so that you also can appreciate more the technical aspects of this. I thought I'd mention it.
What does that look like to you, Jarvis? Not unlike an island. In which case, the place over here. Highlight the insert. Who's the full cuts? You're ready.
What does it look like to you, sir?
I'm discovering, correction, I'm rediscovering the element. Loose landscaping, the shrubbery, the trees, parking lots, exits, entrances. Destruction of protons and neutrons using the pavilions as a frame.
That's a display system. I want to all those bad, real bad.
There for almost 20 years. Still taking me to school.
The proposed element should serve as a viable replacement for palladium.
Excellent.
Unfortunately, it is impossible.
So that's Hollywood's version of 3D user interfaces, right? One of the reasons why I really, really, really want that display system is he closes his hands and there's light coming out of his hands. Now tell me how the physics of this works. How's that possible? Okay? I mean, forget about if we can do it. Is it possible? But it's a little bit. Basically, the light has to bounce inside there and then bounce out in the specified direction. Without the system, well, actually, the building is there. That's quite interesting. I've shown this clip to some physics profs, and they were like, well, that's interesting. The physics profs go like, So, but this is Hollywood's version of a 3D user interface. Everything works like magic. You know, one of the most telling moments is he takes the Unisphere and then immediately goes like this over his hand. And where did the gesture end there or not? And how did the system know that the gesture ended there or not? As I said, magic. So this is not something that we can have for real at the moment. Okay, this works good in a movie, and this is Hollywood's version of what a 3D user interface could be looking like, but it's far from anything practical. Gesture segmentation is a huge problem. It works in that area. Even in 2D, we can't solve this problem in 2D. But so I'll show you some examples of where we have 3D user interfaces in existence today, and I'll give you a little bit of a characterization of where we want to. Let's start at the top left. Top left is a large screen display of some scientific data. You're increase precipitation over a range. And this is usually used as a collaborative tool. So I have multiple people talk about problems, say, is this the simulation right? Similar, or what does this have impact on the ecosystem? Top right is basically computer-aided design. In this case, SketchUp. SketchUp has a big impact on the field of architecture. We've been writing on similar design environments, interior. And here we're really concerned mostly with the surfaces of the objects that are. We're actually not talking about designs of objects. Bottom left, sun's looking glass. One of the many proposals for 3D window managers, 3D desktops, 3D whatever you want to call it. One of the many of them. Now it tells you how dated this image is because music comes on CDs. Not. Right? It's MP3 today, right? Not CDs, so that tells you how old this is. And this vision of using a 3D desktop has occurred many times in the literature and has been implemented many times and has failed many times. I'm not going to pull my punches here. So far, nobody has found yet a use for 3D window images that actually exceeds anything that we can do. And I'll talk about why a little later. Bottom right, computer games. Now I've picked on purpose not the first-person shooter, because that's what everybody thinks. But actually, first-person shooters are explaining a very interaction poor. Interaction is usually very limited in the first-person shooter. So what I've picked here is a completely different game. This is Electronic Arts Sport, and this is a system that allows, or a game that allows people to create animals, buildings, spaceships, vehicles with a mouse. And I've had my kids use this system. Kids can create this. Right? And you can create slugs in the form of letters, and all weird kind of examples exist what people have done with this one. And of course you play the game, but at least you get to design something. The middle bottom is an example of something that I won't be talking about much. This is volume visualization. This is talking about the interior. So you take a scan of my head, and yes, this is a data set for a scan of a head. I will not be talking that much about it. I will say the following, that it has fundamentally different properties. Our volume visualization methods here are not very good in general. I'll be talking about why. About that. One of the things, do you actually see this skull from the front or from the back? Can you tell? And the answer is no, actually. Can't tell. You see it from the front because of the way your perceptual system, but you cannot decide if it's actually real. Because it's an orthographic projection. There's not enough data. And the top middle is virtual reality. Now, for amusement value, I've picked here a really old virtual reality system. Not one of the first ones, but one of the first ones where we tried to get a little bit more portable and so on. So this is literally two CRTs, two CRTs, and the box in front is not a computer, this is just electronics, and gloves, and all of that. So, this is a very old VR system, but it gives you an idea. Typically, the interaction here in this case is with gloves, especially with these. Because we want to interact with your hands, with our hands, and so on. So, I've been looking at, I looked at this a couple of years back and basically went like, so okay, fine, this is what exists. With your examples, people have been building systems that interact with 3D and spatially and so on. What's working, what's not? What can we do, what can't we do? What is possible, what is not possible? And so I've started to analyze what is possible, both from technical as well as from a human standpoint. So let's start first on the display side, the output side of the whole system. And the first thing that everybody talks about when you talk about virtual reality is you want 3D display. That's great, and how do we get 3D display? Well, typically we get 3D display by displaying two different images. to the eyes of the user. There's quite a few technologies that can achieve that. The simple ones are linear polarization, two different linear polarizations, or circular polarizations, or we do shutter glasses, right? Or some of the other technologies or we do what most many head-mount displays do. We put two monitors in front of two displays, physical displays, in front of the eyes, and all of them are roughly at a high level roughly the same. Now to point out some of the limitations that come with that. Where is stereo? Sorry, this is not just a talk. This is also a quiz. Where is stereo perception most useful? Close by or far a little way? Far distant. Where is it more useful? Close by. I agree. Okay. Here, if you do this test, right, I can see two different images. If there's a mountain in the distance, I say mountain, right? So it's usually close by. So, and I'm making a very general statement here that I know that this is not easily defensible as such. Stereo is most useful within 3 meters of range. It's a rough approximation. So, what Hollywood movies do you know that have most of their content within 3 meters of the viewer? Documentaries, I mean, like landscape and so on. Unless you're looking at films. Action movies. Car flying through the air. Yeah, maybe for a second flying by you, but it doesn't really matter stereo perception that much. The motion cues is pretty strong at that point. You don't really need it. So, funnily enough, the best genre for this, could you stand up for a second? I just need something here, just stay there. Right? Is something like a conversation between two people, or romantic comedy, or something like this, drama. Yet that is not the genre you want for 3D, right? So wait, how does this work again? There's a little bit of a contrast here, and I like to point that out because. So why is Hollywood doing 3D? I know two reasons. Well, you can subject to different glasses. And by the way, it's really hard to film a 3D movie off the screen. So I know two reasons why Hollywood is doing it. But I've seen Avatar in 2D and 3D. It was a great movie in 2D. It was a great movie in 2D. In 3D movies, you typically get the reminder at the end of the movie that you really saw a 3D movie when something is flying right in your face. It's important to remind you why you spent the extra money. But beyond that, the usefulness of stereo is not as great as some people might want to make you believe. I hope that works. Now, talking on the other forms of display technologies that we can use, you see the tiger jumping out of the tablet here, and I will use a page of paper here as a simple example here. So assume this is a display surface, doesn't really matter, right? So what this display does is basically we have the display like this, right? And the light is coming out of here, and the light is coming out of here, stops in midair, and then goes a different direction. Right? Because otherwise the tiger would not show up right beside it. So how's that work? Again, one of those where the physics profs go like, no, don't know how to do that. So that's again a clear marketing image that kind of shows you what you could be, but as such it doesn't work. Now on the top right, you actually have a volumetric display. So this is now a spherical display where there's something spinning inside it. And depending on which system you have, either LED matrix in there or a projector from underneath or something like this, and it's basically projecting glowing points in space, which is cool. Glowing points in space, that's actually pretty much a technology that we saw in the Iron Man movie. One of the things that it cannot display is me. Why? Because you will see the front of my face and the back of my head too. Remember that skull picture I showed you in the very first slide? That's how it will look.
That's the best this display system can display. Because otherwise we again have different amounts of lights in different directions, and this display system can't do that. So a volumetric display is also not the answer. One of the things I want to point out about display systems, and these are limitations, of course, that I point out, but they're often kind of glossed over, and they're important to mention in quite a few contexts, is that many head-mounted display systems have a limited field of view, right? So this is about 90-degree field of view. Okay, if you have that much field of view in real world, you're actually not allowed to drive in many jurisdictions because the periphery of your vision matters a lot for navigation. Right? If you are the HoloLens, 40 degrees field of view. That's augmented reality. That's not virtual reality, but very limited field of view. So there's actually also an impact on the things that you can do on the field of view. 90 is not bad. I'm quite happy with the HTC Vive and similar devices, okay? But if somebody tells me that they're doing a study on natural navigation in virtual environments with this device, I'm going like, yeah, no, you can't. You're missing a critical component that we know is necessary, okay? So that doesn't apply. So the field of view of humans is over 180-degree field of view. Okay, so that pushes what you ask from the display system quite far. Okay? Yes, this field of views are getting larger, but it's also a question of optics. There's several problems there. Bottom right, I have basically put a block up, and can anybody tell me if the text at the top of the block is correct? And the answer is no, because there's not enough pixels. But even with a high amount of pixels, it doesn't really matter. Because the problem is the following, and this is one of the catch-22s here, is how do you read? Well, I read my paper like this, right? If the text is like this, in a galaxy far, far away, oh yeah, the text gets smaller, right? Well, oh, you can do it this way. Well, then the bottom of the text gets smaller. Or you can do it this way, then the right side of the page gets smaller, and thus less readable, right? Or here, the left side of the page gets smaller, and thus less readable. So in other words, information, as soon as you don't have your text like this, information density in general decreases. So I have an existence proof of this, very simple existence proof. Some of the people who are most interested in information density is day traders in a bank. These guys have 8+ monitors on their desk, okay? 4K monitors, 8 4K monitors on their desk, and they want more. And oh, by the way, they make enough money to actually make that worthwhile. If 3D technology was providing a benefit for them, they would have already switched. They haven't. They can afford to buy a $500,000 system. That's not a question for them. With the $500,000 system, they can make $500 million profit. Okay, so $500,000 is change for these people. Yet they are still using 2D monitors. That insight made me think a little bit about what it means to actually display the maximum amount of information. So now if you go back to my question of why the 3D window manager desktops and all of this fail, well, there's no strong benefit to them. Yeah, you can see that the web page is tilted away from me. It uses less space, but that also means less information. So there's no big benefit there. And the other option is, of course, then you can navigate there, but there's a cost in the navigation. And that's something that many people forget. There's a cost in navigation, right? I mean, if I want to go there, I have to walk there. Yeah, okay, now I see it different, right? But I actually have to walk. And walking is a very easy metaphor for navigation. Most virtual reality navigation metaphors are harder than Okay, then a couple more quiz questions. Top left. So how many professions do we know where people are actually doing full 6 degrees of freedom navigation? So what do I mean? Well, 6 degrees of freedom means the following, right? I can move forward, backward, left, right, okay, up and down, right? So that's 3 degrees of translation. And then I can rotate this way, and which one did I miss this time? Sorry. Yeah, so this one, and this one, and this one. Sorry, yes, thank you. Sorry about that. I always, I've done it so many times, I go, which one of that? You will find that rotations around the view axis, so this kind of rotation, is usually very rarely done. There's very, very few systems that do that. And going up and down is also very rare, relatively speaking. In computer games, you typically have to forward, backward, strafe left, strafe right, look up, left, right, right? And then you have to jump and crouch. So I characterize this as 4.5D, typically, right? For simplicity. Right? So how many professions that humans do actually use 6 degrees of freedom? Now I've already put a picture there to give you one profession, astronauts. There's a couple others. Anybody have any ideas? Yes, especially night divers. They lack on navigation cues. They learn special techniques to compensate. Night diving is really scary.
Olympic gymnasts?
Yes, okay, I'll let that, yes, yes. They have a lot of constraints on the problem, right? But because you have to take the physics into account, and it's not as if you can stop in midair and change your direction, right? They wish they could, but physics kind of puts a hard constraint on that. Fighter pilots, within constraints, especially if you have a Harrier jet. Again, within constraints. Any one of those professions has one property: hundreds and thousands of hours of training. You're not allowed to fly an airplane upside down unless you've had the training. Okay, because any slight mistake and boom, airplane in ground. Hopefully you were able to eject before that. So this actually tells you how many people have the cognitive capabilities of doing 6 degrees of freedom navigation freely. You need to train this. It is well known that on the space station, people can easily get disoriented. And NASA worries about this because if a micrometeorite hits, they need to find the exit real quick. And if they get disoriented, we have a dead astronaut. Given how much it takes to get an astronaut up there, that's a real expensive experiment to make. And the other thing is, I actually know a computer game that used 6 degrees of freedom navigation. The last computer game that made any commercial success was 6 degrees of freedom navigation, another pop quiz. Long time ago. More than 20 years now. Descent, 1995. Really old game, I know. Since then, most computer games have 4.5 degrees of freedom. Most successful ones, okay? Of course, everybody tries now. Nothing wrong with that. But that's what works. That's what works. When we create 3D, in the middle top, when we create 3D, we typically build scaffolding. We rarely create 3D in midair. When Michelangelo worked on David, right, he actually stabilizes his hand. You know, it's not like he's chipping on the marble like this. He's most probably stabilizing his hand not to break that priceless piece of marble the wrong way, right? Because it's a simpler problem at that point. And we do that. We simplify our problems. We build buildings in fairly rectangular structures because that's a lot easier than building them freeform. Talk to any construction crew if they have something fancy in a house, how much more work that creates. Also cognitively easier. Okay? All right, another pop quiz. Sorry, just throwing them out here. So this is north. Well, actually, this is north. Could you please point to, let's say, Europe? So where's Europe? Go ahead. That's north for reference. So most of you are pointing this way. Okay, I'll accept this as a solution, except that I will point out that it's down there. Oh yeah, Earth is a sphere. I know I cheated. I set you up. I put a flat projection there, okay? But no, in 3D space, this is the shortest distance to Europe. Shows you again how strong our mental models are biased towards 2D simplifications that actually make life easier. And it's just a spatial cognitive capability. Right? We have made our life easier that way. We built 2D floor plans that make it easy to understand the buildings. And we don't have 3D floor plans. Could we make them? Yes. Have they been tried? Yes. Have they taken off? No. Do we need them? No. There are some special circumstances when we do need them. Absolutely. But in general, no. Our visual perceptual system is fooled easily. So bottom left figure, right? I mean, you have the adult looking to be smaller than the kid. This is just a perceptual illusion. In this case, the room is not straight. Okay? So we can fool our perceptual system fairly easily in some ways. The middle picture is a guy working upside down, doing something down there. And why is he doing that? Because we have a strong tendency to actually, when we work somewhere, especially with accuracy and precision, to look where we work. Right? If I'm somebody assembling a car on a chain for the umpteenth thousandth time, of course I will put the screen like this. Okay? But if I do it the first time, I will bend down and put the screw in, and I will look where my hands are. We typically manipulate what we see. Highly learned actions, for example, me putting on my watch, I don't need to look anymore. Yeah, that, yes. But untrained actions and actions where we need high accuracy and so on, we typically look at our hands, which means we need to see what we're interacting with, which means also that, well, maybe, wait a minute, well, how much can we see? First order simplification, I will just use one eye, right? Everything that you can see with one eye. Oh wait, that's like a picture. That's actually 2D. Yes, you can see more in stereo, right? I mean, the classic example here is this one. I can see this side of my hand with my right eye, right? And this side of my hand with the left eye. Okay, fine, yes. Sure, there's something that you cannot see from a single viewpoint. Out here, that doesn't matter so much anymore. Right? And then last but not least, I want to point out that our interaction is actually quite limited. The tip of a pen is a good approximation for a cursor. Please tie your shoelaces with a pen. I'll give you 2 pens. Hard task, right? Our cursor that is used in many, many, many applications, including virtual reality, is a crude approximation of what you can do with your hands. And I'm not good at this. Okay, I'm not good at twirling this in my hand. I don't know, people will go, spin this around, awesome. Okay, highly learned action again, but what we can do with our hands by far exceeds what we typically use as input devices. And as a first order approximation, a controller is still also like a hand, like a cursor, and how it's often used. So I've been looking in my research also at the input side of things, and that actually I want to spend a little bit more time on the input side of things, because for interaction you also want the efficiency and speed and accuracy in the input. And so a series of PhD master graduate students have looked at what we can do to characterize how good input devices work in 3D. Other people have looked at perceptual aspects and so on. I've specialized on this with my research group. So this is a very early system. This is actually a CRT monitor. Not that we couldn't afford the LCD, you could see it on the left side, but to keep the latency down and to make the measurement apparatus as high performance as possible at that time, we had the 120 Hz CRT, position it flat, instead of using an LCD. At that time, the LCDs were only 60 Hertz. So here what we did, we actually replicated a classic human performance experiment, basic science. How fast can you hit two targets? Fitts law task, really classic task. And we replicated this on the screen, and then we went also above the screen and watched as performance deteriorated. So the experimental task is basically, you see this box that's basically sunk into the display, and the targets either are at the surface of the display or stick out of the display with stereo. Right? So we have stereo, we have head tracking in here. You can see the an older version of an OptiTrack system there. And you can see the pen we used. It has a button so that you can go click, 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 click to indicate selection, right? With a mouse button similar, but it's right on the side of the pen, so it's really convenient. And we did experiments, and we tried to look at how performance changes above the display. And no surprise, it drops off the further away you get from the display. One of the things I want to point out, we use a very well-established, in the meantime, methodology to do this that combines speed and errors into one measure. Because you have a speed accuracy trade-off. And this is fundamental to this problem. You can be a little faster and more sloppy, or you can be slower and more accurate. The measurement of throughput, as defined by an ISO standard, and in fact there's been a revision to this now, there's a new ISO standard around this, but has been well established and allows us to characterize this and allows us also to compare different participants and different input devices. And so that's what we have used here. So Rob Tedder did this as his, was a large part of his PhD thesis around this. We have replicated such experiments on different hardware platforms. In this case, this is now a stereoscopic table with finger tracking, using an optical finger tracking system against stereo glasses, and the same task, and we're just clicking with the other hand, right, to avoid the problem that you need to recognize the click gesture. And if you have any problems in that, that can only decrease performance, so we tried to do this as best as we could. And so here's an exemplar outcome of an experiment. The horizontal axis is the higher, so this is the display is on the left, basically, right? The table surface is on the left, and it gets higher and higher towards the right. And performance is in throughput, which is in bits per second, which basically tells you how well this works. And you can see that two different methods that we looked at here. One of them is selecting in the air. So I have to select the target like in the air, click, click, right? Or I have to select it by touching the screen. When I actually touch the screen. So kind of like simulating a 3D input system with a touch screen. And so we evaluated this, and we found that, interestingly enough, there's a trade-off. Within a few centimeters, the touching through actually works really well. Within about 8 centimeters, give or take, up to 10 centimeters, and then it drops off worse. But you can see that both curves drop off with distance to the screen. And that's a fundamental property, that on-screen interaction is better than off-screen interaction. And you immediately lose about 75%, 25% of the performance, so you're immediately at 75% or something like that. Michelle Brown, one of my master's students, she investigated the leap motion, and initially we actually, you see a little leap motion at the bottom, and initially we actually investigated it like this with finger pointing, okay? That ends up about, best case, 75% of the mouse again, so about 3 bits per second instead of 4 in this specific series of experiments. And so we can say, well, this is not a good input device, okay? And you can train it a bit, and if you train a lot, you get better, so some people can reach nice performance. We found, interestingly enough, that one of the better options for using an input device was a chopstick. So using a pen-like pointing device was actually a good idea. That was one of the highest performance input devices I found. Now this one, you need the other hand with the space bar, but this was one of the better options that we found. Now, other things that we have tried is, this was an experiment together with Max Pfeiffer from Germany. Here we used an EMS system, So electrodes here, right? And basically jerk your finger back as if you hit the target in midair. Okay, and we also had a little vibration motor, so if you hit the target, it just vibrates. Okay, either the finger gets jerked back, and we saw that with this system we could also have good feedback there. It works better if you have the feedback. So if you hit something or not, that works better if you have feedback. But there was no fundamental difference between the EMS and vibration as far as we could see. So, and again, performance was not as good as you would expect with, say, a mouse. Going a little further, I've done, this is now work with Vanessa Wiebert and Jeremy Cooperstock from McGill, where we investigated now not just pointing or selection and pointing, which are very similar task, but in this case now 6-degree of freedom manipulation. So now your task is the following: you want to take this object and you want to put it over here. Or as a docking task, you want to take this object and dock it here, right? Put it exactly in the right orientation. Oops, and hopefully it doesn't fall down. Right? Put it in the right orientation. And so here in this experiment, we compared 4 different input devices, and the 4 different input devices are first on the bottom, in the middle of the bottom, is a 6-degree of freedom input device. That's a pen. It's a haptic input device. Actually, you can force feedback on this pen, except that in this case we didn't use the force feedback. We only used it as an input device. Okay, so there was no feedback in the sense that the robot would push you back. It's a little robotic device, basically. Then we basically used the pinch gesture, where we track the hand position with optical hand tracking system, and the pinch gesture so that we can basically grab something in midair and rotate. We also used the mini chair, that's the top right, middle top, a replica of the chair that we were using in the task. Basically grab a chair and put it in a particular different pose, right? And so we used the replica of the mini chair because previous work had reported that this is a great idea to have a direct one-to-one replica. So we tested that by tracking the chair and seeing if that would work. And then again, it was kind of interesting because that was roughly at the same time as Michel's work. We also came up with this idea of testing a pen-like device. And so we actually tested a pen here, and we did track the pen in 3D, including the rotation for the pen. And that turned out to be actually an interesting thing. And I'll talk about that in a second. So in general, the mini chair and the air pen were the fastest alternatives. The Phantom, the mechanical input device, was the most accurate. People liked the air pen quite a lot. That was our best rated input device. Now why? Okay, some of the issues are around accuracy, because with the hand you can do the coarse manipulation quickly, but doing it accurately is a lot harder. You actually can, with a pen, express the rotation better. Right? So if you want just a rough manipulation, grab it, put it there. If you want fine manipulation, that's not as great. And that's what really came out of this work, right? The interesting part about the pen was that the rotation around the 3rd degree of freedom, you can roll the pen with your fingers. And that turned out something that people liked. Turned out that people liked this one. So I've looked at other aspects of 3D interaction. Just give me 1 second here. We came up, and this is our collaboration with Sujin Zhang and others at Purdue. We actually came up with a way to characterize fatigue for 3D interaction. And so the issue here is the following. You're interacting like this. Can you tell me how fatiguing this is? There's something in the literature, the gorilla arm effect, that if you do this for 8 hours a day, you get real tired. And if you look in professions in the real world that actually work like this for 8 hours a day, you will find there are none. Because even the conductor does this at the beginning of the symphony, right? And then does very quickly this, right? Because otherwise this gets very tired. Right? This gets very tiring. So we came up with a novel methodology to actually measure the strength of muscles The reason why we needed to do that was because previous work here uses dynamometers and other devices that are fairly expensive and fairly specialized, so we came up with a simple way to measure the strength, a methodology to measure the strength of people, and then came up with a three-state model for the muscle activation and how fatiguing things is, and found that this actually fairly accurately predicts how fatiguing a user interface can be. So we can actually model today a user interface, the fatigue effects of a user interface. So we can compare two interfaces and say this is more fatiguing than another. In limited circumstances, because you need to do this for every muscle that's involved, right? So now if you have interfaces that require all of this, that's a bit more work, right? In this case, we only looked at a fairly large scale point, but found that generally predicts quite well. We have looked at things like if you see your arm in VR. So this is now a system where we actually, free selection in a VR system, and you see different representation of your arm. You either see only a hand until the elbow roughly, and then the whole hand. And the interesting part about this is static targets and with moving targets and all of this. One of the interesting outcomes of this is that the whole hand representation actually performed worse, which is kind of counterintuitive. But apparently it was not believable enough, or something didn't work, so that people actually preferred seeing only the hand, or the hand of it. It was a counterintuitive result. We published this towards the end of last year. So how do we make better 3D user interfaces? I've looked at some of the input devices, right, and basically found that there is nothing that competes with a mouse and thus also with a touch screen, because mouse and touchscreen are roughly equivalent. Pen as well as an input device, high-end pen, like on a Surface or something like that. But what other properties are there that can make it easier for us to create great 3D user interfaces? And so there's a couple of observations that I want to list here that are important. So the first thing is no floating objects. How many things in 3D float? I'm not doing a mic drop here. But how many objects around you float in midair? In this room? In this city? Right? Yes, floating objects are the exception. And there's nothing wrong with that, except that every VR system, or not every, but most VR systems, most computer-aided design systems, the default is that everything floats. What's wrong with this picture? Yeah, I'm being very critical. We do not understand how humans work, thus we make everything so that it's easy to program, and not how humans actually work. That's not good design in my book. And I'm being very critical here, and I understand that some people might get upset if I say this, but I'll just point it out. As a designer, you learn that you actually need to look at what your users can do and what their mental models are. And my mental model is there's drums, right? Sorry for the artifacts in the sound recording here. But, so no floating objects. And I will show you some interaction methods in a little bit that actually take this into account. Then we have cars that have collision avoidance. But yet it is very easy in many VR systems to take this pen and stick it into the table. That makes it harder to actually put the pen down on the table like this. You can't have it both ways. Right? So having everything interpenetrate everything else makes it hard to align things, which we're used to doing. Look around you how regular this environment is. Right? Things are pushed together, aligned with each other, and so on. If we allow things to penetrate all the time by default, then that's not such a great idea. On the other hand, I don't want physics. I don't want things to fall and break. Okay? That's also not. Because we're in a virtual environment. Why should it break? Unless it's the objective of what we're trying to do, right? So breaking things is not necessary. Right? So I'm not arguing for the full physical simulation. I want a smart environment. That's what I'm arguing for. The other thing I pointed out earlier already. So if we know that people like to look where they manipulate, why do we need to support tasks where they can't see what they manipulate? As a first-class citizen, we don't really. There's no fundamental motivation for me to be able to adjust something at the back of the monitor if it makes everything else more complicated. It's a trade-off, and that's what I'm doing. I'm pointing out that there's a strong trade-off here. And you can have it one way or the other way, but you can't have it both ways. You need to think about that as a designer. Perspective. Textural cues like the pattern here on the carpet. All of these things provide strong depth perception. Motion cues provide strong depth perception. There's a lot of cues to 3D that have nothing to do with stereo. So it's okay not to have to support stereo in every situation. Andy Wilson was pressed at that point at a conference where he gave a talk, and he basically said, well, it's not always necessary either, right? And this is Microsoft research there, right? He said, no, yeah, it's a VR system, and it's very immersive, but doesn't do stereo, so big deal. Sometimes not having stereo actually makes things simpler. And by the way, a lot of 3D TVs, many high-end TVs don't support 3D anymore. That's another issue. Please keep the lag down. One of the things that I don't have time to talk about is we did measurements of what happens when you have lag in the system, how that affects performance. I can tell you it's bad news. For interaction, not for navigation, not only for navigation. With navigation, it makes you sick. With interaction, it slows your interaction down. And we can see this in our experiments. We can see the performance drop. And you can measure this, you can quantify this. Top left, I want to point out, look at where the cursor is. I want to point out that the cursor is an artifact. If I grab this block, and I look and I concentrate on the position of the cursor, according to the cursor, and assuming now I'm using a contact assumption for the moment, then that block should be one layer behind, right? It should be actually on the second surface there. Yet we found in experiments that no, people expect this behavior. The cursor doesn't matter. It's the whole object that moves that matters. So we have played with methods, and there's some deep research in this. I mean, if you really want to go into really, really, really basic science here, if you look at what happens when a monkey grabs a tool and manipulates the tool, which part of the brain lights up? It is not the tip of the tool. It's the whole thing. You're paying attention to more than just the point. So for good interaction, use that. So in this case, we use actually the area behind an object. Top right, use constraints when you have them, right? Like a wheel rotates naturally around an axle. So use that. Make it easy for the user. Similar bottom left. If we have 2D construction aids in real world, there's nothing wrong with 2D construction aids in 3D. There's nothing wrong with that. And it actually helps, because it also helps the mental model. People are used to it. They understand this better. Okay. And lots of VR drawing systems quickly go from, oh, you can draw everywhere, to, oh, you can draw on a surface, on a flat surface, or on a curved surface, depending on what you want to do. And then for navigation, and I've said this before, I'll say this again, well, 4.5 degrees of freedom is a good solution. Support that. You don't necessarily need to do this. Well, with a head-mount display, it's cheap to do this, but people don't do this in the real world much. Right? So using these lessons, we've done some work on better methods. And I'm showing them here on desktop systems. We've taken some of these into VR systems. This is a sliding metaphor where you basically slide another object on the surfaces behind it. Now this is actually technically interesting because there's a whole layer of computations happening, but this actually works very well. So when the object, before the object disappears, we actually pop it to the front so that it never can get lost, targeting novices with this system. Okay, I'll just play this clip again. Sorry, for some reason it doesn't loop right now anymore. We pop the object to the front so that it cannot get lost. That's an important property that makes it easy, but otherwise it slides on whatever surface is behind it. And that means, and it doesn't really matter what the direction of the surface is, right? I mean, that means the object will slide up the wall and slide on the ceiling. It will just always stay attached to something. So this is not a physics gravity constraint. This is not a gravity constraint. This is much more than that. Okay? It will slide on a diagonal wall, happily. Okay? Or a slanted ceiling, like in here. Right? And that simplifies interaction. Now, how do you do this? What we actually do this is lots of, we actually use the frame buffer for the computation. So there's a lot of computation happening in the background here. We identify which object is behind the moving object and then find the right depth and snap it to that depth and so on. And all of that is done in the frame buffer instead of doing geometry calculation. But you could do this in geometry as well. I'm not going to talk about this. So if you do this, you can do things like a puzzle video, a puzzle task. So this is now a 3D puzzle where we have implemented a method with rotations, with the mouse here in this case, where we're using the right mouse button for rotations and the scroll wheel for the third degree freedom, which works fairly well. And so you can see you can solve a puzzle task here with a mouse fairly fast. It is not real time, this is sped up by a factor of 2, but it's fairly rapid to do this. In fact, for the 3D user interface contest in 2011, this was the fastest solution presented for the puzzle. Here we have a little problem with the collision detection, so that's why we have to take that piece out first and then put the other piece back in. But this is a way to show what this can do. Okay, and so because it makes it fairly easy to fairly accurately assemble this puzzle. Okay. Now, one of the things that I want to point out, we did this, and then we asked people to do the real task, as in a real wood puzzle. Yeah, with the real wood puzzle, we took half time, even if they were using one hand only. So we have our work cut out still, but this is one of the best solutions that we can do at the moment. Okay. I'm not going to show this one, in the interest of time. Going beyond sliding, with shift sliding, we can actually basically hit the shift key and lift up from whatever surface we're on, and then slide parallel. And that works quite well. So here we're sliding off the wall, basically. And we can move this. And as soon as there's a collision, it reverts to the basic sliding behavior so that we always stay consistent in the system. We've implemented this way. And you can, again, put the object anywhere you want, right on this side surface, and it will slide relative to this surface, right? So it's a context-sensitive slide here. And if you move the other way, you can actually push objects into other objects. So now you're sliding inside other objects. But again, this is an explicit action that the user has to set. You have to hit that shift key, otherwise it doesn't work. And that goes with the principle, that this is an exceptional circumstance. I don't think you can see it very well here, but we can even slide on a point cloud. So this is now basically like LiDAR data, right? Point measurements, and we can slide here on a point cloud just as well as on geometry. So we could do this for a 3D scan data. Let's just show this up there. With depth pop, we use the mouse wheel. Everywhere, say a long corridor, you have multiple doors, right? That could stand in every door. Click, next door, click, next door. And one scroll wheel. And so we implemented this here, and I'll have another video here that shows this a little bit better in a more complex scene. So here we have a ring in a tree, and now the ring can be in any position where the ring is around the branch or touching a branch. And you hear the click for every iteration of this, and the system tells you, no, you can't move there when you hit when you hit the maximum, right? Because otherwise it would disappear into the distance or jump too close to the lever. So we limit that to make it easy for people to understand how the interaction works. So this is again simplifying 3D manipulation, right? Making it easy for people to move objects. Here you can see how the sliding plane changes when you are over very irregular geometry, right? And even in this case, there's multiple solutions, as you can see, right? And the object is never in collision with the scene. So it's always in contact with the scene. And it's always resolved in the frame buffer, how we do that. So this is, I think, over 1 million triangles right here. Making navigation simpler, here's a method that we presented at WIST in 2015, where we actually orbit around an object. We make it easy to move around an object and keeping a constant distance to an object. So previous work has, this is HoverCam here, has outcomes that look like this, and you can see this is not a good result. So with ShowCam, we actually managed to smooth these irregularities in the movement out and actually come up with a camera path that makes more sense for a human, where the jerk and other measures are actually objectively less, which are positive attributes. And so here the camera starts and stops. And so we define this better and come up with a camera motion that's not as jerky, right? And that comes up with a way to make it easy. We also deal with more complicated scenes when there's multiple objects, because here, depending on the distance to the object, you can orbit around the smaller object, or if you orbit a little further away, like in the bottom, you actually orbit about both of them together, right? The Earth and the Moon type of thing, right? Or satellite. Right? And so we did an experiment how people like this. This is, for example, the existing method with this jerky and stickiness and our method provides much smoother navigation around orbiting out of the object. One of the application scenarios is here that you stay at a certain distance to the object so that you could draw on the surface, say, right? If you want the texture of the surface. Right? Here is the technical method, what's happening in the background. In the interest of time, I'm not going into the details here, but we're actually pre-computing the path and then deciding exactly where the user can move on which manifold. And then this of course, also works with more complicated geometries, as we will see in a second. Bunny is done. So you can create very good camera paths around fairly complicated geometry. Yes?
Is the path being generated automatically, or is
so we can do both. Okay. We're targeting this at interactive orbiting. Okay, and that's how it was published. But can we generate a path? Yes, we can generate a path. Okay. All you do is basically you follow the path, follow the solution, basically. Right? That's all you need to do. I've also experimented with speed control. This is an early experiment in this direction, so that you can see this is a huge environment, right? And we're flying through this, and the speed is controlled by the system. The direction is controlled by the user, but the speed is controlled, and we're radically slowing down at the moment, right? Because there's stuff around us, and so we're radically slowing down, and here we're flying through a crack. And so the system slows us down. There's a lot of braking here, and then once you get out here, the system actually speeds us up quite a lot. And so this is a navigation method that allows us to traverse environments that have largely varying scales. Okay, it's not perfect; it's more jerky than it should be, and this is something that we're currently working on. But it gives you an idea that you can do similar things for free navigation. Stop this here. So something that. To finish off the talk, there's two systems that I want to kind of talk a little bit about. This is TIVES. This is a cave system that we've built. This is actually something that we showed at BC Tech. Right? This is basically a frame that's hanging on the ceiling, 8x6. You roll the screens down, you turn the projectors on, and you're in a cave. And you can, This is designed for multiple people sitting in here, right? So that multiple people can experience virtual reality together. One of the interesting properties of the system is that it doesn't do stereo. Through a coincidence, we bought these projectors, and the projectors nominally can do stereo, except there's no graphics card that supports this projector because of the timing signals that the projector requires. So that was a little disappointing right there. And so that's, it's still very immersive once you turn the system on and you start navigating because of the motion, the full 360-degree field of view of the motion. It's very immersive. And so people can easily experience this as a virtual reality system. Targeted at having 3 people sit together, and that could be a kitchen designer and a couple or something like this, or 3 friends playing a game together or whatever, or a show floor or something like this. But once you roll the screens up, the system is gone, right? And it hangs 7 feet from the ceiling, so you can easily hang it once and forget about it. And this is something that I just showed at BCJ. Some people have seen recently there. And last but not least, and this is a little bit with a laughing and crying upgrade, why that I present this is a large display wall. It's actually casters, so we can move these displays around. So these are 7 4K displays that are working at 60 hertz off a single computer. And the reason why I have a crying eye here is because right now, due to an operating system upgrade, the system is broken. I cannot demonstrate this right now. Tomorrow I'll go in the office and see if I can fix it again, but this is right now not working. But it's a cool display system because one of the things you can do is actually take the displays and actually arrange them around the user. You can actually physically move the displays and build a cave this way. They're actually stereo capable, so this is one of the last generations where pretty much the TVs, high-end TVs by default supported a 3D display. So these are actually, we can use them as stereo displays as well. So it's a large display one. And I'd like to say, well, where am I going in the future? Well, augmented reality, hand interaction. Clearly we're investigating these interfaces. We're also measuring them. Interaction with drones is some of the aspects that we're looking at and figuring out what the best interfaces might be. And last but not least, I really need to thank my students because without them I couldn't have done this. And this is just the ones who contributed most to this work. Okay, there's clearly the other members of my lab have contributed in various aspects to this work as well. And of course the funding sources. I'd like to thank you for your attention.
Great.